everyone, I'm Diego Ochoa from Power SmartCtrl, and today I'm going to show you how to design the control loop for the three-phase inverter with a LCL filter. First of all, I want to show you brief information about the SmartCtrl software. So let's start. So SmartCtrl is a tool that allows to design in an intuitive and simple way the control loop of any types of power electronic converters. This tool is very useful in sectors such as education or industry, for example. SmartCtrl adapts to different levels of knowledge because there are three ways in order to define the converter plan. I will show you later what is the three ways that I mentioned. Once the control loops has been designed, we can export some parameters to third-party simulator. In this case, in this moment, SmartCtrl is linked with PSIM or Simba in some topologies. And also in SmartCtrl allows you to design controls in continuous domain for analog controls or discrete domain for digital controls. So when I open the program, this is the initial dialog that appears. And as I mentioned before, we have three ways to define the converter plan. The first way is called the predefined topology that are in this region of the window. And in the predefined topology, you can find DC-DC converters with different type of control structure. For example, you can select the option with a single loop in order to control, for example, the output voltage or the inductance current. Also, you have a control structure for the peak current mode control in DC-DC converters, and in DC-DC converters, also you can find the option if you want to implement a double loop or average current mode control. For the case of the PFC, we have two options in the predefined topology. One of them is for the single phase PFC, and also we have the three-phase PFC boost converter that you can make the controls in alpha beta domain or DQ domain, for example. In this example, I showed the average current mode control, and in this window, you can see the design flow of the SmartCtrl. The first step, you have to select the plan. In that case, we have different topologies. For example, you can find the buck converter, boost, buck boost, flyback forward, full bridge, and dual active bridge. After that, you have to you have to define the sensor stage. In that case, the inner loop regulates the inductance currents. So we have different type of current sensor. Then we have to define the compensator for the inner loop. We have SmartCtrl has three type of predefined compensator. You can find the PI, the type 2, type 3. And also there is a tool that we call equation editor that you can write the transfer function in an analytical way of your own compensator. So after that, we have to select one point of the solution map. The solution maps represent the relationship between the crossover frequency and the phase margin. And in the weight region, you can select one point, and this all the solution that ensure that our control will be stable. After select one point for the solution map for the inner loop, we have then to define the sensor stage of the outer loop. In that case, we are controlling the output voltage. We have different type of voltage sensor. Then we have to select one of the predefined compensator for the outer loop. In that case, also we have the PI, type 2, type 3, and also you can use the equation editor. After that, we have a second solution maps, and here we have to select one of the possible solution of the outer loops. The second way is to, in order to define the converter plan, we call equation editor. You can find in this region of the window. And here you can write the analytical transfer function of the converter plan. So in this option, perhaps you have to know some modeling techniques in order to get the transfer function. and you can write here. This is a very powerful function because here you can define the converter plan for any type of power converter, electronic converter. So after that, this equation editor can accept a transfer function in S domain, Laplace domain, in order to design the control loop for analog control. And also you can define the transfer function in discrete domain with the C variable. So in that case, in order to, for example, design the digital control. The last way in order to define the converter plan is it's called the import frequency response, and you can find this option in this part of the window in the initial dialog. And here is a very useful when, for example, if you already have a simulation schematic and you can, for example, PSIM, in that case, you can use the ACC function in order to get the frequency response of the converter plan. In that way, you can save the points of the body in a TXT file, and then you can import this information directly to SmartCtrl. So another option, for example, if you have a real prototyping or real converter, also you can use a frequency response analyzer in order to get the frequency response, and then you can import this information to SmartCtrl. So this is the last way that you can define the converter plan. In SmartCtrl, when any of the parameters are modified, all the results are updated immediately. So in SmartCtrl also have another tools that it's called parameter sweeps. And here you can change, this is the input parameters of the power stage, for example. And here you can change the value with a slider, for example, the value of the input voltage, the inductance, capacitance, etc., in order to make a sensitivity analysis. That means that you can, if you move the input parameters, you can see how affect the dynamic of the system. As I mentioned before, the solution maps, this is the solution maps, and you can see here that represent the relationship between the crossover frequency and the phase margin. And also, if you move the cursor through the white region, you can see how that all the body plots and transient response will be updated automatically. So as you can see in this figure. After that, if you already select one point, you can access to the reports, the output data. In that case, if you select, for example, a type 3 compensator in analog form, SmartCtrl recommend you some values of the passing element, like resistance or capacitance, in order to achieve the zero frequency and the pole frequency of the compensator. So also you can see the information of the frequency of the zeros and the poles. Also in SmartCtrl, all the waveforms, for example, the transient response of the frequency response, you can export or save this information in a TXT file. If, for example, if you want later to make some post-processed analysis. So another option that SmartCtrl has is the exporting option. In that case, for the predefined topology, SmartCtrl can create a PSIM simulation and also Simba's simulation in order to check if the control loops that you select, the solution that you select for the control loop, will be stable. So for Simba, you can use this. You can export to Simba several of the predefined topology. Not all, but we are working that you can export all the predefined topology to Simba simulator. Also, in the installation folder, you can find some examples. There are some tutorials in order to guide you step by step how to design the control loop, for example, using the predefined topology, or using the equation editor, or for example, the frequency response, import the frequency response. So in each tutorial, you can find the PDF documents that it's the step by, you can find the step by step how to design the control loops, and also you can find the files, for example, the simulation file, in that case for PSIM, and also you can find the smart control file in order to see the bandwidth of the compensator. So in the smart control user guide, also you can find in a docs folder, you can find the smart control user guide and the what's new. The what's new, you can see what is the new features of the latest version of the smart control. So in this slide, we have a summary of, and you can see here that we have some links that guide you to the YouTube channel, and here you can see the webinar that we made before. And also we have another tutorials with a collaboration with Altair, for example. And here you can see what is the link between PSIM and smart control. So we have a lot of materials in order to guide you how to use smart control. So now it's time for the live demo. And today I'm going to show you how to design the digital control of the three-phase inverter with a LCL filter. So the three-phase inverters are widely used in applications such as motor drive and renewable energies, etc. And also the LCL filters are used in applications where very low THD for the current is required. So one of the main considerations that we take into account for the LCL filter is that the LCL filter plan is a third order transfer function. So when we design the current loops, we have to take into account the resonance peak of the filter in order to ensure that our system will be stable. So in this live demo, we start from a PSIM simulation. Also, I try to explain a little bit the theoretical transfer function that I want to use in the equation editor on smart control. So here, after that, in smart control, we design the current loop of the three-phase inverter, and finally, we export some parameters in order to check in the transient response if our solution or the point that I select in the solution map ensure the stability. So let's start. So this is the main transfer function that we have to take into account in the digital control. The first is the current plan. As mentioned before, we are controlling the grid current. So the transfer function that we need to know is the modulating signal to grid current. So this is the transfer function. Here, it's this transfer function takes into account some of the parasitic resistance of the elements. And also, if you can see here that we have a third order transfer function. So we rearrange this expression in order to is more easily to write in the equation editor. So these both transfer functions are the same. So this is the plant, the converter plant. Then also we have to consider the modulator gain. In the modulator gain depends of the peak value of the carrier signal. In that case, the carrier signal is triangular. So we need to know the peak value of this carrier signal. So, and also depends of the input voltage in that case for the three-phase inverter. Also, in the modulator transfer function, we are included the delay due to the digital control. So in that case, we are sampling the inductance currents two times per switching frequency. So as you can see here, this is the switching frequency. and we are taking account, we are sampling the current at the vertices of the triangular current. So as you can see here, this is the sample key, the clip plus one sample, etc. So also we are assume that between the samples we have enough time to make the ADC conversion and also the calculation of the equation, the different equation of the PI, etc., and the part transformation, etc. Also, the control that will be implemented is in a DQ frame. So sorry, this is a DQ frame. And in the transport delay is composed by two parts. The first one is related to the calculation times. So we are taking the ADC and the calculation. As you can see here, this time T1 is fixed and is equal to half of the switching period. So this is the first part of the time delay, and also we have to contemplate the second part that is related to the DPWM. So in that case, we have a double update because we are updating the modulating signal 2 times every switching period. So as you can see here, so we are updating half switching period, and this delay is also fixed. That is equal to the quarter of the switching period, so for double update. So in that case, the transfer function of the modulator, we have the static gain of the modulator, and also we are taking into account the transport delay. And here you can see here. For the sensor stage, we have to contemplate, for example, in order to your sensor, your magnitude is inside the span of the ADC, you have some signal conditioning stage. In that case, we are considering just a simple low-pass filter, as you can see here. This is for the analog stage. And then we have to contemplate or take into account the gain of the ADC. So the gain of the ADC depends on the bit number and also for the span of the ADC. So the total transfer function of the sensor stage that we have to write in the equation editor in the SmartCtrl is this one: the multiplication of the low pass filter and the gain of the ADC in that case. For the PI compensator, this is the analog transfer function of the PI compensator. Also, the PI compensator will be discretized by the backward Euler method. This is the transformation. And then we can, in SmartCtrl, we will know the key P and the TI parameter of the PI. And then we have to transform these values to the coefficient of the difference equation of the PI compensator. This is the difference equation of the PI using the backward Euler method for discretized. So finally, this is the control structure that will be implemented in the simulation, PSIM or SIMBA, and also, as you can see, we have the PI, so the transfer function, the PI compensator. Is this one that we have to use, the equation editor, the different equation, sorry. Also, we are compensating the gain of the modulator. So in that case, the transfer function that we have to take into account is just this one, the delay, because we are compensating in the control structure the static gain. Also, for the sensor, we are assuming unity feedback because in the digital control it's very common to compensate the inverse gain of the sensor change. So in that case, as you can see, we are compensating the static gain of the ADC and also the static gain of the analog sensing chain. So in that case, the transfer function that we have to take into account in SmartCtrl is just the frequency of the pole. So let's start. Let me open a SmartCtrl software. Here, I go to File and to the initial dialog. Here, I have to go to the Design Generic Control System. In that case, we want to define the converter plan in equation editor. So this option. And here we have to, if you click on editor, here you have to write this transfer function, the converter plan. So this one. I already have this transfer function in a TXT file. So I want to copy this and paste it. Okay, here we have the inputs parameters, the power stage. We are also considering the delay, the digital delay. This is the transfer function for the digital delay. And finally, this is the transfer function of the converter plan. So it's the digital delay multiplied by the current plan, as you can see here. And also in the equation editor, it's important to write the return function in order that to select the transfer function that SmartCtrl will be used in order to design the control loops. So in that case, I have to click OK. After that, in the switching frequency, in that case, we have a switching frequency equal to 40 kilohertz. Click on compile. And as you can see here, we have the third order transfer function. We have the resonant peak here of the LCL filter. And then we have a phase drop due to the LCL filter and also for the digital control. So we have two phase drop in that case. So then we have to click on OK. Now it's time to define the transfer function for the sensor stage. So in that case, as mentioned before, the transfer function that we have to use is this one, just the pole. So in that case, I already have this transfer function here. Maybe editor and paste. Also, this is the cutoff frequency of the first order low pass filter. Click on OK. Again, the return function. Compile, click on compile, and you can see here the frequency response of the first order low pass filter. So in that case, you can click on OK. After that, we have to define the compensator. In that case, I select the option for the PI compensator, as you can see here. And we have to select the gain modulator equal to 1. Remember, because we are compensated in the control structure, the gain of the modulator. So in SmartCtrl, the modulator gain is calculated by this expression that depends of the peak value and the valley value, and also for the rise time and the switching period. So in that case, if I set a peak value equal to 1, valley value equal to 0, and rise time equal to the switching period, you can define a gain of 1. So in that case, I have to select in here 1, 0, and 25 microseconds. After that, I have to click on OK. And then we have to select one point of the solution map, for example, here. Click on OK, and that's it. So in the LCL filter, it's important to take into account, as I mentioned before, the resonant peak of the transfer function. So in that case, if we select, for example, this point of the solution map, it's possible that our control will be unstable, because in that case we have different zero crossing. As you can see here in the second zero crossing, the phase is below the minus 180 degrees. So in that case, it's possible that this solution will be unstable. And also we have a third peak that is less than the second peak. The phase is less than the second peak. So in that case, we have to reduce the bandwidth of the control loops. In that case, for example, I select 1 kilohertz and 50 degrees. As you can see, in that case, we only have one zero crossing. That this is the crossover frequency. So this is we have here the crossover frequency and the phase margin that I selected here. So this is a good solution. And in that case, this is the key P parameters and the TI of the PI compensator. So as mentioned before, the PI compensator in different equation is represented by this equation. So in that case, we have to calculate the coefficient of the different equation. So I have in our Excel sheet here, I have to copy the values of the values that the SmartCtrl give me. So for KP, it's equal to this point -3, and TI is equal to 237.345 -6. The sampling frequency in that case is twice the switching period, so it's equal to 12.5 microseconds. So in that case, we have the coefficient of the equation difference, the difference equation here. So I will open the PSIM simulation. We have here the power stage, as you can see. This is a converter connected to grid. And also this is the control structure for this type of converter. So this is in analog way. So we have to include some elements in order to take into account the main things that appears in the digital control. So the first step, I have to add the zero order Hall, as you can see here, zero order Hall for all the magnitudes. In that case, the switching frequency is twice the sampling frequency is equal twice the switching frequency. And here. So I have to copy to all the magnitudes. Here. Okay. So another thing that we have to include is the digital delay. In that case, I used the block that is called unity delay. So I put here the unity delay, and the sampling frequency is equal 2 times the switching frequency. Again. Again, we have to copy to the Q-axis. And the last step, I have to change the analog PI transfer function to the discrete transfer function. So I have to add elements, control, digital, C domain transfer function. So we have to write this transfer function. So in that case, the coefficient is Kc and minus Kc multiplied by Rc. And in the denominator is equal 1 and minus 1. The sampling frequency equal 2 times the switching frequency. Okay. Copy this to the Q-axis. So we have this is the reference, 40 amperes for the D-axis that control the active power, and 0 amperes for the Q-axis that control the reactive power. So in that case, I have to copy the values here. Let me move to the next screen. I have to put here 0.1 and also 9.5 minus 1. Okay, and now save, and it's time to run the simulation. So we have to wait some seconds. And we have to see if our solution is stable or not. So let me open. This is the modulating signal. The modulating signal is stable, so we have to see the currents, the three-phase currents, and you can see the three-phase currents achieve the reference, and our control is stable in that case. So the last step I want to make here in the PSIM simulation is I want to measure the frequency response of the open loop transfer function. So in that case, I have to go to others, AC sweep. I have to add a perturbation here. This is the sine source. And also here we have to peak value 0, frequency 0, and the names vSyn1. This name have to be equal to the source name in the AC sweep configuration here. The amplitude equal to 1 in that case. And we want to measure from, for example, 700 to 10 kilohertz. Okay, save. And we have to add the proof, the ACC proof, in that case, the loop ACC proof. So we have to add here. And now it's time to run the simulation. So this takes some seconds. We have to wait a little bit. Remember that our crossover frequency is equal to 1 kilohertz approx. So here you can see that the crossover frequency is around 1 kilohertz. So we can view data point, files, save as. So in that case, I want to compare. I save this in a TXT files. Now I want to go to SmartCtrl, disable the converter plan, and this is the open loop transfer function. So I want to import, in this option, import merge. Click on add the T function, and I want to select the TXT file that I save. So click on OK. I want to change the color, black, OK, click on OK, and finally apply, and click on OK. As you can see, both transfer function match. So this is the frequency response from PSIM and the theoretical transfer function that is the pink trace. So now I want to repeat the procedure for Simba simulator. In that case, in Simba, we already have the power stage, and also this is the sensing change and stage. So in that case, we have a transfer function for the first order low pass filter with a gain equal to 1. And in that case, we have to add the zero order hold. So I have to go to the library, control, and then go to discrete blocks and select the zero order hold again. So in that case, zero order hold here we have to define the sample frequency. So the sample frequency, the sampling time is equal to 12.5 microseconds. Okay, I have to copy this to all the magnitudes. Okay, so again, we have to add the delay. In that case, we have to select this block, the delay block. So put here. And also the sampling frequency, again, is equal to 12.5 microseconds. And the delay length is equal the same, 12.5 microseconds. So I have to copy this for the Q-axis. And also, in that case, we have to replace the analog PI compensator for the discrete. So in that case, again, we have to use the discrete transfer function here. And the sampling time is equal to 12.5 microseconds. And for the denominator, again, we have 1 and -1, because remember, we have to implement this transfer function. And for the numerator, again, in the calculation sheet, the Excel that I have, I make the multiplication of both parameters. So in that case, I have to copy these two. Kc is equal to 0.551. And for the multiplication of the Kc by the Rc is equal to 5.24 E minus 1. And this is negative. So again, I have to copy this to the Q-axis. I want to save the project. And finally, I have to run the simulation. So I run the simulation. Result, we are going to the result, then transient. And for example, we want to see the modulating signal. This is the modulating signal. In that case, the Carrier sign, the peak value of the Carrier signal is around 10. So is inside the modulating signal are inside in this range of value. So if we click on new chart, also we can see the currents, the three-phase currents. Again, we can unify the three-phase current, and also, for example, you can see the theta or the DQ components of the grid voltage. So in that case, we are in this simulation, we are aligned with the D axis. And here you can see that the Q component of the grid voltage is equal to 0. So that is all. Thank you very much for attending to this webinar. And if you